So we will start with logic gate, the fundamentals of logic gates. Then we will use this logic gates to design logic circuit. So logic gates, basically it will have two or more inputs, as I written, two or more inputs, but only one output. Of course, these are nothing but electronic circuits connected in various ways. That is what is called as logic, and depending upon that, the output will be either 0 or 1. The output will be either 0 or 1 depending upon the logic applied at the input. When I say logic applied at the input, it's nothing but the various types of connection which we make, electronic connection which we make. Of course, you will understand when I'll go through all the gates one by one. So for a logic circuit, the basic definition will be: a logic circuit is an electronic device where the output is either 0 or 1 depending upon the logic applied at the input. I'll repeat the definition. Logic circuit is an electronic device where the output is either 0 or 1 depending upon the condition or the logic applied at the input, depending upon the way in which the inputs are connected. So that is what will be the definition of logic gates. The logic gates will be further divided as, we call it as types of logic gates, further divided as basic gate and derived gate. Under the heading of basic gate, we will study three gates: AND gate, OR gate, NOT gate. Whereas under the heading of derived gate, it will be NAND gate, NOR gate and exclusive OR gate. These are the fundamental gates, and using these gates we can design the derived gates: NAND, NOR and exclusive OR. Now, after understanding basics of logic gate, we will start with the first type of logic gate called as basic gate. Under this heading basic gate, we will try to understand three gates: AND gate, OR gate and NOT gate. Now the names are little bit difficult to understand, but once you understand the operation of the circuit, you will be able to relate the name, that is AND, OR and NOT. So that is what we will try to understand. For all these three gates, AND, OR, NOT, we will try to understand these 6 points. Simulator circuit. Simulator circuit means a circuit which operates like that, operates similar to the circuit which we are trying to understand. It is not exactly the same circuit, it is like the same circuit. It operates like the same circuit. So that is what will be a simulator circuit. Then on the basis of simulator circuit, we will write these two things: truth table and definition of that gate, then the symbol, then the equation, and then the timing diagram. Timing diagram is nothing but graphical representation of the truth table. So one by one I'll take a gate and we will try to form all these things. We'll try to understand all these things about that particular gate. So the first gate which we are trying to understand is called as AND gate. AND gate. And for that, the simulator circuit, I hope you understand the symbols which I'm going to use. I'll explain, of course. So we are designing a simulator circuit for AND gate. Of course, you understand that this is a symbol for DC source, a potential, a voltage source. These two are switches A and B. And what you can understand is these two switches are connected in series. And the output will be indicated by a bulb. We name the output as Y. Now, these are the two inputs and this is the output. All the examples which we are going to take will be of 2 input and 1 output. As I said, logic gate can have more than 2 input, but the output will always be 1. Now the switch will be in only 2 conditions. Either it will be on or it will be off. When I say on, that means it is a closed switch. I'll just take an example and make you understand. If I close these 2 points, we say that the circuit is closed switch. That means it is working in on condition. And if you keep it open, that means no connection between 2, that means the switch is off. So switch will have only 2 conditions, either on or off. We say either closed or open. And if you apply binary logic, remember binary number system has only 2 symbols, 0 and 1. As I said, we understood that number system so that we can apply that number system in this logic circuits. So switch, either it will be on, it will be off, it is closed, it is open. We say when switch is on, say it is represented by binary 1, and when switch is off, it is represented by binary 0. Similarly the bulb will be on or off. That means it glow or it doesn't glow. So we will again give 2 binary combinations for say bulb is on, let's say the output is 1. When the bulb doesn't glow, the output is 0, or the bulb when it is off, the output will be 0. That is what is the basic consideration for all the gates, AND gate, OR gate and NOT gate, and all the derived gates also. Now on the basis of this, we can write the truth table. We are done with simulator circuit. Let us try to understand the truth table first, and then we will go for definition. So truth table is nothing but tabulation of input and output. So this is your truth table. Now there are 2 inputs, A and B, and the possible combination of A and B will be either 0 or 1. That means these are binary combinations. So total number of possible combination will be 0, 2 raised to power 2, that is 4 possible combination. So when you write the possible combinations of A and B, we write nothing but the first 4 numbers of binary number system. It is 0, 1, 1, 0, 1, 1. You have to keep this combination as it is. Of course, we will write in 2-bit binary number, so this number becomes 0, 0, 0, 1, 1, 0, 1, 1. This combination has to be kept in the same sequence as I have written on the board. It will be 0, 0, 0, 1, 1, 0, 1, 1. So this is nothing but the logic which we are going to apply, and the logic will work depending upon how the inputs are connected. As I said, the inputs or what you can see is the input can be connected, the input is connected in series. So now say for the first condition, when A and B both are 0, what happens? Switch, when it is 0, switch is 0 when it is in off condition, that means open state. So the switch are in open state. Now when the source is applied, current will flow through the circuit, but current will flow through the circuit only when the switch are closed. The circuit has a closed path. But when both the switches are open, will there be any current flow through the circuit? Of course not. If there is no flow of current through the circuit, bulb will not glow. If the bulb doesn't glow, that means output will be 0. That means Y will be 0. Understood? When A and B, both the switches are open, no current will flow through the circuit, bulb will not glow, and therefore output Y will be equal to 0. Next, A0, B1, A0, B1. Now what happens is, out of these two switches, A is open, B is closed, but they are in series. Just look at the circuit and tell if there is any current which will be flowing in the circuit. Of course not. If any one of the switch is open, the circuit is break. So no current will flow through the circuit. So if no current is flowing, bulb will be still, it will not glow. So output will be 0. Next 1 0, A is 1 and B is 0. When A is 1, B is 0, still as they are in series, circuit is not completed, no current will flow through the bulb, bulb doesn't glow, the output Y will be equal to 0. And when both the inputs are 1, that means both the switches are closed, the circuit gets complete. The current will flow through the circuit. When current flows, the bulb will glow, and when the bulb glows, the output will be 1. So this is the logic for AND gate. That means when any of the two inputs, if it is 0, the output is always 0. When both the switches are 1, that means when both the switches are on, only then the output is 1. That will be the definition of AND gate. When both inputs are 1, the output is 1. If any one input is 0, the output is 0. So that is the definition of AND gate. The next is symbol, equation and timing diagram. Symbol, the symbolic representation of AND gate is like this. Just make a D. These are the two inputs A and B, and this will be your output. Now look at the truth table carefully. What you can see is AND gate amounts for, if you take binary multiplication, it amounts for binary multiplication. 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1. So Y will be A and B, and A and B is connected by a dot. The dot sign here indicates AND gate. Of course, AND gate is similar to multiplication, but the dot sign here indicates not multiplication, it indicates AND gate. That means A and B are connected by an AND gate. So it is very important that you understand. So this is your symbol, and this is your equation. The last part of this is timing diagram. Timing diagram, as I told you, it is a graphical representation of truth table. So we draw such lines. The lower line indicates 0, the upper line indicates 1. So first we will draw for A. What is A? 0, 0, 1, 1. So two lower lines and two upper lines. So 0, 0, 0, 0, 1, 1. A is 0, 0, 1, 1. Next B is 0, 1, 0, 1. So draw B. It will be 0, 1, 0, 1. So it is nothing but the graphical representation of the truth table, and then you have to draw the output waveform. So Y will be 0, 0, 0, 1. What is the logic for AND gate? When any one of the input is 0, the output will always be 0. When all the inputs are 1, only then the output will be 1. So when you draw the waveform, this is 0, this is 1, 0, 1. So for 0, 0, the output will be 0, 0, 1, the output will be 0, 1, 0, the output will be 0, and for 1, 1, the output will be 1. So this is timing diagram for AND gate circuit. The next basic gate is OR gate. See the modification which I am going to do on the circuits. The second circuit is OR gate. in this circuit I'll change the logic. That means I'll change the way in which the switches are connected in the circuit. Let the two switches be connected like this, and you can see the diagram and easily understand that these two switches are connected in parallel now. In AND gate the switches were connected in series. In OR gate the switches are connected in parallel. Again the same condition will prevail. Switch on, output is we will consider it to be 1. Switch off, we will consider it to be 0. Bulb glows, we will consider it to be 1. Bulb doesn't glow, we will consider it to be 0. Again, how many inputs? 2 inputs. So in the truth table, how many possible combinations we will have? 4. 0 0 0 1 1 0 1 1. So now see the output according to the inputs which we have applied. See the condition. When A and B both are 0, when both inputs are 0, that means when both the inputs are open, दोनों input अगर open है, so will there be any flow of current in the circuit? Of course not. So if no current is flowing in the circuit, bulb doesn't glow, the output Y will be equal to 0. Now A is 0 and B is 1, that means A is 0, B is 1, that means now what happens is, now the current which will be flowing will have a path to flow through B, through bulb to the ground. That means the circuit has a complete path through B. So when A is 0 and B is 1, current will flow through the circuit, bulb glows, output Y will be equal to 1. Next, A is 1, B is 0. Now the circuit gets complete by A. So current will flow through A and to the ground through bulb. So bulb will glow, output Y will be equal to 1. And when both the inputs are 1, of course current can flow through A and B both and through bulb to the ground. So output Y will be equal to 1. So this is the truth table according to the simulator circuit of OR gate. And what you can see is, of course, we have done the addition part of binary numbers, binary arithmetic. 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, and 1 plus 1 we consider it to be 10. Now if you remember that addition rules and compare it with the truth table of OR gate, 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, but 1 plus 1 in addition it is 10, but in OR logic it is 1. So the truth table of OR gate almost resembles the binary addition part. So we consider it to be, so equation when you write for OR gate, we write Y is equal to A and B, and A and B is connected by plus sign, where plus sign indicates not addition, plus sign indicates OR operation. OR operation is similar to addition of binary number, except the last condition, when both the inputs are 1, the output there it will be 10, here the output will be 1. As the output is 1 when any one of the input is 1, that means OR operation, right? A or B, if any one of the input is 1, the output is 1. When both the inputs are 0, the output will be 0. So accordingly we will modify the definition when both the inputs are 0, the output is 0. If any one of the input is 1, the output is 1. This is the definition of OR gate. Next is the symbol. The symbolic representation of OR gate will be like this. Draw a curve like this, okay, and join these two curves. So this is A, B, and this is Y, and Y is equal to A plus B. That means A and B connected by OR gate. And the last one is the timing diagram. Timing diagram, again as I said, it will be a graphical representation of the truth table. A is 0 0 1 1, so it will be 0 0 1 1. B is 0 1 0 1 0 1 0 1. And now what will be the output Y? It is 0 1 1 1. So when both the inputs are 0, the output is 0. And if any one of the input is 1, the output becomes the output becomes 1. So this is timing diagram of OR gate. The last one under the heading of basic gate is NOT gate. It is also called as inverter gate. Look at the circuit diagram and you have to understand that this is the only exception. When we wrote the definition or understood the definition of logic gate, we said it will have 2 or more inputs but only 1 output. So of course output will be 1 for all the gates, but we said 2 or more inputs. This is the only exception. NOT gate has only 1 input, and that 1 input is connected in parallel to the bulb, and we call this as short circuit. Let us try to understand what exactly I mean by short circuit. Of course this switch either will be on or will be off. When switch is off, that means the switch is open, will there be any flow of current through the circuit? Of course not. That means it has a high resistance path. And when the switch is closed, the current will flow through the circuit or flow through the switch. That means it has low resistance or zero resistance path. So in electronic terms, any path in an electronic circuit where the resistance becomes zero, that path is called as short circuit path. So we are trying to create a short circuit in parallel to the load resistance. Now very important to understand is that when the current flows in parallel condition, current will flow like this. It will flow through the bulb, it will also flow through the switch. In parallel combination, the current distributes. So now it has 2 paths to flow, either through the bulb or through the switch. Let us consider the first case. When A is 0, A is 0 means switch is off condition, switch is open, and when switch is open, it provides high resistance path. So if it is a high resistance path, current will flow through the bulb. Of course no current will flow through the switch, but current can flow through the bulb. The circuit is complete here. The current will flow through the bulb to the ground. That means current will flow through the circuit, bulb will glow, output Y will be equal to 1. And when A is 1, that means A is 1, switch is on, it is closed condition. So when it is closed, what happens is suddenly the switch provides a short circuit. Short circuit, that means a path in an electronic circuit where the resistance is 0. So of course current always takes least resistance path. So all the current now will flow through the switch. No current flows through the bulb because bulb provides high resistance. So now all the current will flow through the switch to ground. No current will flow through the bulb. So if no current is flowing through the bulb doesn't glow, the output will be 0. So when A is 0, the output is 1. A is 1, the output is 0. Therefore it is called as inverter gate. So when you write the definition, when input is 0, the output is 1. When input is 1, the output is 0. It complements the input. So NOT gate complements the input. Complements means 0 will be converted into 1, 1 will be converted into 0. Symbolic representation, draw a triangle and a bubble sign. This is a symbolic representation of NOT gate. Equation, there is only one variable. So what we will do is y is equal to a, and over a we will draw a bar sign which indicates complementing the variable a. If a is 0, the output will be 1. If a is 1, the output will be 0. So this is called as complementing that particular variable. So any variable which has to be complemented, it has to be connected to a NOT gate. And lastly, the timing diagram, a, this is 0, this is 1, y will be, when a is 0, y is 1, and when A is 1, Y is 0. So this is timing diagram for NOT gate. Next is derived gate. That means we will use the basic gate to form another type of gate called as derived gate. Under the heading of derived gate, we will try to understand two gates today, and in the further class we will extend one more gate called as exclusive OR gate. The two gates which we will try to understand is NAND gate and NOR gate. So this is the first one, that is derived gates, NAND gate. What you can see is, again, the two switches are connected in series, but they are connected in parallel to the bulb. So now when the current flows like this, it will have two paths. Either it will flow through the switches or it will flow through the bulb. So it will have two paths because current in parallel combination divides depending upon the resistance value. Now in the first case, again the two conditions will remain same. Switch on will represent 1, switch off will represent 0, bulb glow will represent 1, bulb doesn't glow will represent 0. So accordingly the truth table will have four possible combinations: 0 0, 0 1, 1 0, 1 1. Now for 0 0, that means both the switches are off condition when the switches are 0, open condition. So will there be any flow of current through the bulb? Of course not. So all the current will flow, will there be any flow of current through the switches as they are open? This path is braked. So the only path left for the current to flow through it is through the bulb. So current will flow through the bulb and no current will flow through the switches. So if current flows through the bulb will glow, the output will be 1. Similarly, when A is 0, B is 1. Now out of these two switches, one is closed, one is open, but still as they are connected in series, no current will flow through the switches, all the current will flow through the bulb. So output Y will be equal to 1. Similarly, A1, B0, B0, still as they are connected in series, and if any one of the switch is open, the circuit is braked, so all the current will flow through the bulb, so output Y will be equal to 1. And when both the inputs are 1, what happens is, now the circuit is complete, a short circuit has been created, so all the current will flow through the switches, because under short circuit condition that particular path has the resistance 0. So all the current will flow through that switches to ground and no current will flow through the bulb, so output Y will be equal to 0. So the output of NAND gate is 1 1 1 and 0. Last condition, when both the inputs are 1, the output will be 0. If you compare the truth table of AND gate with OR gate, if you compare the table of NAND gate with the truth table of AND gate, what you can see is it is exactly opposite. For AND gate, the Y output was 0 0 0 1, and what you can see here is it is 1 1 1 0. So if you apply a NOT gate after an AND gate, what you are going to get is exactly inverse of this 1 1 1 0, which is nothing but NAND. So AND followed by NOT is NAND gate, and that is why it is called as derived gate. And followed by NOT is NAND, that is why it is called as derived gate. So how the definition we will write? Definition we will write by using truth table. So when both the inputs are 1, the output is 0. If any one of the input is 0, these three conditions, the output is 1. So this is the definition of NAND gate. Next, the symbolic representation. As I said, how we define AND gate? It is AND followed by NOT. So first you draw the symbolic representation of AND, and then for NOT we write a bubble sign. So you write a bubble sign for NOT operation. Similarly, the equation will be y is equal to, as I said, and followed by NOT. So symbolic representation of and will be a dot b, and for NOT operation we draw a bar over it, a complement over the variables. So it will be a dot b whole bar. And what will be the timing diagram? Timing diagram, the output is 1, 1, 1, and when both the inputs are 1, the output will be 0. So the timing diagram will be 1, 1, 1, and for the last condition, the output y goes to 0. The next derived gate is NOR gate. See the modification which I am going to make for a NOR gate. In this case, the two switches will be connected in parallel, A, B, and they are connected in parallel to the bulb. So all these three variables are in parallel. So current, when it will flow, and up to this point it will flow through A also, it can flow through B also, and it will flow through the bulb, of course depending upon the condition of switches. Again, as there are two inputs, we will have four possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. Consider the first condition. When both A and B are 0, switch 0, that means it is open condition. When both the switches are open, will there be any flow of current through the switches? Of course not. So all the current will flow through the bulb. So the output Y will be equal to 1. Next, A0, B1. A0, B1. Switch 0, A is open, switch 1, matlab B is closed. So out of these two switches, B is closed. As soon as B is closed, a short circuit is created. We mean short circuit created means the resistance through that path is 0. So what happens is all the current will flow through, no current will flow through the bulb, no current will flow through A, all the current will flow through B to the ground. So as there is no current flowing through the bulb, the output Y will be equal to 0. Next, A1, B0. So A is closed, B is open. Open means high resistance path. So now as A is closed, all the current will flow through A, no current will flow through B, and no current will flow through the bulb also. So output Y will be equal to 0. And last case, when both the inputs are 1, current can flow through A and B. That means short circuit is created by either A or B, but no current flows through the bulb. Output Y will be equal to 0. So output of NOR gate is 1, 0, 0, 0. Now if you compare this table with the table of OR gate. So what was the table of OR gate? 0, 1, 1, 1. And if you apply a NOT operation to this, what will be output Y? 1, 0, 0, 0. It will complement the values. And what you can see is 1, 0, 0, 0 is the output of NOR gate. So what is NOR gate? How we design NOR gate? OR gate followed by a NOT gate will give you a NOR gate. So how we'll write the definition? When both the inputs are 1, the output is 0. If any one of the input is 0, the output is when both the inputs are 0, the output is 1. If any one of the input is 1, the output is 0. So this is the definition of NOR gate. Symbolic representation, first we will draw OR. As I said, NOR gate is OR followed by NOT. So first we will draw the symbolic representation of OR and then a bubble sign over it to give OR followed by NOT. So this is a symbolic representation of NOR gate. Equation Y is equal to A plus B. A plus B indicates OR operation, and if you draw a complement over it, A plus B whole bar, complete bar, that is complete complement, will be nothing but NOR gate. And what will be the timing diagram? 1 0 0 0. So when both the inputs are 0, the output will be 1, and for all other condition the output will remain 0. So that is the second of the derived gate, that is NOR gate. We'll have transistor as a switch. So when the transistor has to be used as a switch, as I said, you cannot connect it in saturation and cutoff, you cannot manually change. So what is the polarity which has to be applied? This is the polarity. Emitter base junction should be forward bias and collector base junction should be reverse bias. Of course, what we have done is we have applied two external potentials, two external biasing potentials which has been applied, but the same circuit can be designed by using single potential. This is what plus VCC, that means VCC indicates collector potential, the total collector potential, VCC. So that is the single potential. RC is the collector resistance, RB is the base resistance. Emitter is common for input and output, so this is a common emitter configuration. Input current will be base current and the current flowing through the transistor will be collector current. Now see what happens is, suppose if I apply at this point, I will apply 0 volt. What does that 0 volt means? 0 volt means no potential. That means it is as if I have connected that particular input base terminal to ground. So if I connect the base terminal to ground, what happens is the base current will become 0, right? And this is common emitter configuration. In common emitter configuration, beta is IC upon IB. Beta is IC upon IB. So can I write IC is equal to beta IB? And the same thing. And as I said, then 0 volt is applied. What happens is the base current is 0. When base current is 0, IC is 0. And when no current is flowing through the transistor, that means IC is 0 means this is the IC is the current flowing through the transistor. So no current is flowing through the transistor. And when no current flows through the transistor, we say the transistor is working in cutoff region. That means at this point the transistor is in off state. No current is flowing through the transistor. So when 0 is applied, 0 volt, the transistor is in off state. See, now what happens is, suppose if I apply 5 volt. Now for 5 volt some base current will flow. Some base current will flow. That base current multiplied by beta. Now what is beta? Beta is 300. So IC is equal to 300 times IB. So for 5 volt small base current will flow and that will be multiplied 300 times to provide IC. That means large amount of collector current is flowing through the transistor, and when the transistor is conducting heavily, large amount of current is flowing through the transistor, we say the transistor is working in saturation region. Okay, so that is how the transistor can be used as a switch. When you give 0 at the input, the transistor is in cutoff region. When you give any higher voltage, the transistor will directly go into saturation region, because collector will be 300 times multiplied by base current. So collector current will be very large. Even for a small base current, collector current will be large. So we can say the transistor is conducting heavily, therefore the transistor is working in saturation region. So transistor can be used in both the one of the two region, cutoff and saturation. So that is how transistor can be used as a switch. Next is, we need for see all these things we are trying to understand chapter number 3, which we have skipped. In that we will try to understand two types of logic families, TTL and CMOS. For TTL, the transistor which we are going to use is BJT, bipolar junction transistor. This is what is bipolar junction transistor, because current conduction is because of both the charge carriers, electrons as well as holes. So now for TTL logic, the transistor which we use has multiple emitter. The transistor which I have told you at present has only one emitter. So now we have to understand how a multiple emitter transistor is fabricated. So this is what is the transistor. Two PN junction diodes are used. This is terminal T, this is transistor with one emitter, this is base,
and this is the resistance, and this is the power supply. Now what you can see is, for this two diode, this is the P region, this is the N region, this is the P region, this is the N region. So both P regions are connected to positive already. So if whether these diodes are forward bias or reverse bias depend upon the N region connection, and the N region connection depends upon A and B. So in a digital, A and B will have 0 0 0 1 1 0 1 1, and 0 corresponds to 0 volt, 1 corresponds to any higher voltage. So when I say A and B both are 0, that means A and B both are grounded, which indicates that P is for both the diodes. P is connected to positive, N is connected to ground. Both the diodes are forward bias. Both the diodes are forward bias, and when they are forward bias, they are acting as a switch, on switch. So this point T gets connected to ground. So potential at point T will be 0 volt, and if 0 volt is applied to the base of the transistor, 0 volt, the transistor is in cutoff region. The transistor is in cutoff region. Similarly, A0 B1, that means A is still grounded, B is plus 5 volt. Now what happens for this lower diode? Both the junctions are connected to positive terminal, so it will be acting as a off switch. No current will flow because there is no potential difference for current to flow. So we say the transit diode is reverse bias. But as A is grounded, T gets connected to ground through this diode because it is acting as an on switch. So potential at T still will be 0 volt. The transistor will be still in cutoff region. Next, A1, that means A is positive and B is ground. So this diode is reverse bias, open switch. This diode is forward bias, on switch. Point T gets connected to ground through the lower diode. That means potential at T will be still 0 volt. The transistor is in cutoff region. Now what happens when both the diodes are 1? That means both the diodes are reverse bias. So now T cannot be connected to ground through the diode, as both the diodes which is acting as a switch are open. So T gets connected to plus VCC. So potential at T will be plus VCC, and if positive supply is applied to the base of the transistor, small base current will flow multiplied by 300 times, large amount of collector current will flow. The transistor is said to be working in saturation region. So this is how basically that circuit works, and that circuit can be fabricated like this. So the two diodes can be imagined to be the extra emitters. So emitter 1, emitter 2, emitter 3. So basically emitter 2 and emitter 3 are what? These are nothing but the PN junction diodes which are connected externally. So that is how these two diodes can be fabricated to have multiple emitter in a transistor. So this is the basic construction of a multiple emitter transistor. Let us try to understand the operation of that multiple emitter transistor, because this is what we are going to use in a TTL logic family. So see, this is A and this is B. How many possible combination for A and B? 1 0 1 1. Now when I say A and B both are 0, that means both A and B are ground terminal. What happens to this PN junction? Both P regions are already connected to positive, N region are connected to ground. So both the PN junction is forward bias. That means current will flow like this, and this current will flow and it will go to ground, either to diode, upper diode or lower diode. So what happens is, if you take the potential at this point, which is the base voltage of your transistor Q1 say, so what happens is the base is connected to ground through the diode, because diode is forward bias and they are acting as a closed switch. So the base is connected to ground, so base voltage will be 0 volt. Similarly, A0 B1, A is still grounded, B will be plus VCC. So now the upper diode is forward bias, lower diode is reverse bias. If any one of the diode is forward bias, current will flow through that diode to ground. Base will be connected through diode to ground. So base voltage will be 0 volt. 1 0, same condition will prevail, 0 volt. and 1 1, that means when both the inputs are positive, both the diodes are reverse bias. That means both the diodes are acting as an open switch, so no current will flow through the diode. Now B is connected to which polarity? Plus VCC. The potential and base voltage of transistor Q1, base voltage of transistor Q1 will be plus VCC. So you can see, if you convert this as digital output, 0 volt corresponds to 0 and any higher voltage is considered as 1. So it will be 0 0 0 1, 0 0 0 1. And that means when any one of the input is 0, the output is 0. When both the inputs are 1, the output is 1. It is similar to AND gate. It is similar to AND gate. So this is how transistor can be. Actually, basically gates are designed using transistors. So this is how transistors works as, or you can make the transistor to work as gates. So this is what is the basics of the entire transistor. This is what we are going to use in TTL, transistor logic.